All right, so let's continue our discussion of partial derivatives in thermodynamics. Um, this time we just covered the second law, so we're going to extend that discussion to the second law. Let me see, full screen. All right, so now that we've gone over the first law and the second law, we can combine those two laws into one equation, which we would call the fundamental equation. If you remember, the first law says delta U is Q plus W, right? So if you have a small change in a small amount of heat flow and a small amount of work done, dQ and dW, okay, then du would be equal to dQ plus dW. So if you were to imagine a reversible process, okay, then du is, we say, is dQ plus dW. But what is dQ for a reversible process? If you recall, for a reversible process, ds is dQ over t, right? So dQ is just t times ds. So that's dQ right there. And what's dW for a reversible process? It's just negative p external dV. Since it's reversible, it's just going to be negative p dV. So this is dW, negative p dV. So we say this statement right here, du equals tds minus p dV. That's your combined statement of the first and second law. Okay, so that would be the energy change for a step in a reversible process. What does this tell us? We know that U is a state function, right? So this is an expression that looks like you have U, okay, a change in U. Okay, we're expressing a change in U in terms of change in S and a change in V. So this suggests then that U, we say, is a function of two independent variables, S and V. So we say S and V are the natural variables for U. Those are the variables that naturally come out from the first and second law. Okay? So what do we know about a function of two independent variables? If U is a function of S and V, we can write then du is equal to something times ds plus something times dv. What partial derivative goes here in the first one? Partial of u with respect to s, holding what constant? Volume constant. What partial derivative goes here in the second? Partial of u with respect to v, holding what constant? Holding s constant. Well, that's in general, right? If u is a function of s and v, then that's generally true. Okay, so we compare that with du equals tds minus p dv. So now we can add to our list of partial derivatives that we can easily measure. Partial of u with respect to s at constant v. What is partial of u with respect to s at constant v? It's just temperature. Okay, that's just temperature. And what is partial of u with respect to constant s? With respect to v at constant s? Negative of the pressure. Okay, so we can say here then that temperature is partial of u with respect to s at constant v, and negative of the pressure is partial of u with respect to v at constant s. Okay? So if I were to ask you, in this classroom, what is the partial derivative of the internal energy of this classroom with respect to its entropy? This classroom is at constant volume. Whatever the temperature of the room is. Okay? So that's your partial derivatives that you can get from that fundamental equation. Okay? Now, how would you calculate delta U if S is constant and V changes from V1 to V2? This would be what happens if S is constant. So you want uh, something at constant s. What are we trying to do? Get delta U at constant s, right? So what would I have to integrate? I'm changing my volume from V1 to V2. So what's my differential here? My integral dv. And what partial derivative would I have here with respect to v at constant s? And what's partial of u with respect to v at constant s? Negative p. Okay. So this is just going to be integral of negative p dv from v1 to v2. And that's just work, right? So adiabatic, right? Q is 0. That's why it's just work. Okay? So we say that a reversible adiabatic process is an isentropic process. Okay? Remember, this is formula that you use for a reversible process. Right. How would you calculate the delta of the process is not reversible? You just need to identify the initial state and the final state, and then imagine it happening reversibly. Remember, u is a state function, so you can always go from whatever you have identified as your initial state to your final state. Imagine a reversible process for doing that process, and you should get the same delta u. Okay? So that's how you apply that. Okay. Now let's talk about a Legendre transformation. Oftentimes, we've found in several cases before that there's more than one way to represent things, right? Like, for example, in Cartesian, if you have a point on a plane, you can represent it with a x and y values, right? Your Cartesian coordinates. Or what's an alternative way? You can use r and theta, polar coordinates, right? Now, a Legendre transformation is just another way of representing a function, okay? So if you have a function y, it's a function of x, okay? We can define a new function w so that w depends only on dy dx, the derivative of y with respect to x. So y prime here is the derivative of y with respect to x. In other words, we're replacing it with another function so that the other function just depends on the derivative of y with respect to x. This might be something you want to do if you don't like x, if you don't want to deal with x. Okay? And the way you would do this transformation is basically this way. So we define w as the original function y minus the variable you want to get rid of, which is x, times the derivative of y with respect to that variable you want to get rid of with respect to x. Okay? So let's illustrate that with this example right here. Let's say y is equal to x squared. Okay? Let's say you don't want to deal with x for some reason. And so let's do a Legendre transformation. Okay? What's the derivative of y with respect to x? 2x, right? So derivative of y with respect to x is 2x. That means, what is x then? X is equal to y prime over 2, right? So x is just y prime over 2. Okay. Now, I'm going to define my w. W is y minus the variable you want to get rid of times the derivative of y with respect to that variable. Okay, so y minus x times y prime. But what is y in terms of x? Y is just x squared. Okay, so x squared minus, what is x in terms of y? In terms of y prime, it's y prime over 2, and then there's y prime right there. Okay, and like I said, I don't like x, right? So what do? I don't like that x. I'm going to replace that by y prime over 2. And what do I end up with? I end up with y prime over 2 squared, that's your x squared, minus y prime over 2 times y prime. So that becomes what? Y prime over 2 squared is y prime squared divided by 4. And y prime over 2 times y prime is y prime squared over 2. So you end up with the expression that says, if you combine these two, this is y prime squared over 4 minus y prime squared over 2. So 1/4 minus 1/2 is negative 1/4. So here your w, we say, is negative y prime squared over 4. Okay? So let's visualize what that is. Okay? So what's a plot of y versus x squared? When x is 0, y is 0, right? When x is 1, y is 1. When x is 2, okay, so 1, 2, 3, 4, y is 4. Same thing when x equals negative 1, y is 1. When x is negative 2, y is 4. It's a parabola, right? Okay. Now let's examine this point now, which is represented by 2, 4, right? X is 2, 2 squared is 4, y is 4, right? What's an alternative way of representing this point? Well, we're going to replace that. So this is your x, y. We're going to replace that by w and y prime. Okay? So what's our w at this point? What's our y prime? 2x. So what is 2x? 2 times 2, which is 4. Y prime is 4. Okay? So that's your slope, right? That's the slope of the tangent line, correct? That's the slope of the tangent line. Okay. What would happen if I were to subtract, okay, x times y prime from y? That's my w, right? So what's my y? 4 minus, what's my x? 2. What is my y prime? 4. So that's 4 minus 8. That's negative 4. You can see that, what's the equation of this tangent line here? What's the equation of this tangent line? The slope is what? It's 4, right? So what can we say then? For this tangent line, the y value would be what? Mx plus b, right? So if I were to subtract mx, I would get b, right? Mx from y. So but y minus mx is really nothing more than y minus xy prime, right? Because my slope here is y prime, correct? So this is really, b right here is really nothing more than the intercept of this tangent line. So there's a point, and then the intercept is going to be negative 4 right here. That's your w. In other words, okay, oops. In general, if you have a curve, okay, if you have a function, and you have a point there, the slope of that tangent line and where it would intersect your y-axis, this is going to be your w. The slope of that is y prime. So instead, we did a transformation then. Instead of representing this curve by x, y, values of x and y, we're going to be representing it by values of w and y prime. Okay, actually, let's switch that to make things consistent by y prime and w. Okay, so we're replacing our y, our function y, by a function w. Note that y and w have the same unit. Okay, because it's the same type of quantity. W is just the y-intercept in this representation. Okay. So that's the whole idea behind a Legendre transformation. When did we do a Legendre transformation in our previous lessons? We did that when we defined enthalpy. Okay. If you look at, remember we said now that energy, the natural variables for internal energy are S and V, right? And we said that du equals TdS minus PdV. This is our fundamental equation, right? Well, let's say we don't want to deal with volume. We'd rather deal with pressure. So we're going to substitute a variable. We're going to do a transformation. So we have a function. We're going to define a new function that naturally depends on pressure instead of volume. So what would be my Legendre transformation? I have my original function minus what? What partial derivative would I have? Let me put that over here. I'm going to say h is equal to the original function u minus something times, what's the variable I want to get rid of? Volume, right? So multiply by what? The derivative of my function with respect to that variable that I want to get rid of. So partial of u with in this case, since we have two independent variables, I have to specify that I'm holding the other one constant. So partial of u with respect to v at constant s. Right? But what did we say partial of u with respect to v at constant s is? We've already identified that earlier. That's negative p. Okay. Partial of u with respect to s is negative p. V with partial of u with respect to v at constant s is negative p. Okay. So what we did then in doing, so this is negative v times negative p is just equal to u plus pv. Okay, so by defining h, we're really just looking at your system from an alternative point of view, you can say. All right, so h, you can see, has the same unit as u. All right, and so what would be our dh then? It's going to be equal to du. What's the derivative of a product? Differential of a product. First times the derivative of the second plus the second times the derivative of the first. So pdv plus pdp. Okay. But what did we say du was? It's tds minus pdv, right? And so to add to that, pdv plus vdp, and what do we get? We get dh is equal to tds plus vdp. So essentially what happens when you did your Legendre transformation, you just switch the roles between the variables that you're switching, right? So remember, I don't want to deal with volume, I'd rather deal with pressure. So this ends up being plus VDP, okay? But now I have a new function that I have to use. This time I'm calling it H. So DH is TDS plus VDP. Okay, so this is a consequence of a Legendre transformation where we're replacing volume by pressure. So it's U plus H is U plus PV. Okay, let's apply that. Let's say I don't like entropy. I don't like entropy because it's not something I can easily measure in the lab. Okay, so I want to replace that by temperature instead. So when I do that Legendre transformation that way, I end up with a function called the Helmholtz energy, given by the symbol A. Okay, so the Helmholtz energy is given by the symbol A. So what would be my Legendre transformation here? How do we do a Legendre transformation? The original function u minus the variable you want to get rid of, which is s, times the partial derivative of the original function, which is u, with respect to the variable that you want to get rid of, holding the other variable constant, in which case volume. What's partial of u with respect to s then? Well, what's partial of u with respect to s? We've done at constant v. We've seen that earlier. What was it? Partial of u with respect to s at constant v is temperature. Okay? So we say that the Helmholtz energy is equal to U minus ST, or U minus TS. It's the more common way it's written. Okay? So if dA is U minus TS, if A is U minus TS, what is dA? It's du minus TdS plus S dt. Now what is du? We're gonna keep repeating this, so by the time we're done today, you should have you'll have memorized this. It's TdS minus PdV. That's dQ minus plus dW, right? Okay, so minus TdS, and that's minus minus, so minus S dt, right? So what's the net result? The TdS cancels out. Minus PdV minus S dt. Let me write negative S dt first. Minus PdV. That's our dA. Okay. How about this one? Same idea. Okay. We're doing a Legendre transformation where we replace, instead of, we don't like S, okay? So in the expression for H, we want to do a transformation so that we have T instead of S. So what do we do now? We say that 1 G is equal to H minus, what's the variable we want to replace? S. And what's the derivative you multiply it with? Partial of H with respect to S, holding pressure constant. Well, what's partial of H with respect to S at constant pressure? I'll go back to the expression for dH. What happens there? Partial of H with respect to S at constant pressure. Pressure drops out. What would that be? It's just T, right? So this is just going to be equal to H minus TS. So you can see this, the similarity. So U is a function of S and V, right? A is a function of T and V. And H is a function of S and P. G is a function of T and P. Okay, so in going from U to A, you're doing a Legendre transformation. In going from U to H, you're doing a Legendre transformation. In going from H to G, you're doing a Legendre transformation. Okay? You can also imagine that you could do a Legendre transformation going from A to G. Okay? So those are, what would be the expression for dG then? If dH, let's go back up here. You should be able to quickly determine what the expression for dG is based on this. What did we do? What transformation did we do from H to G? We replaced S by T, right? So we're going to switch roles for S and T. So instead of TdS, you're going to have negative S dt plus VdP. Okay, so dG is negative S dt plus VdP. Why? G is Gibbs energy. You've encountered this in freshman chemistry, and so this is something you know that we use a lot in chemistry. Why do you think that is? Why is it so convenient to use that function? Look at your independent variables. Temperature and pressure, things we're very familiar with, things we can easily control or measure in the lab. Okay. All right, so you can say that in the energy representation, the fundamental equation is du equals TdS minus PdV. Now, the expression dH equals TdS plus VdP, what happened here? What transformation did we do? We switched the role of V and P, right? Remember we said H is U plus PV. So this expression right here, dH equals TdS plus VdP, that's what you would call the enthalpy representation for your fundamental equation. Okay. So in terms of the enthalpy here expression, what is our T? What partial derivative is equal to T based on this expression for the enthalpy representation? Partial of H with respect to S holding what constant? Pressure. Your independent variables here are S and P, right? What about volume? What partial derivative is equal to volume based on this? Partial of H with respect to pressure holding what constant? S. The other independent variable is S. Okay? So, let's say you wanted to know delta H at constant S, if S is constant, and P changes from P1 to P2. How would you calculate delta H? At constant S, integral from P1 to P2. So, what's my integrand here? D, P. What partial derivative goes in here? H with respect to P holding what constant? S. But what is partial of H with respect to P at constant S? That's V, right? So integral of V dP from P1 to P2. Okay? Right? What would that be for an ideal gas? Integral of NR T over P dP from P1 to P2. Okay, can we factor out T? Constant S, T is not constant, right? You don't know if T is constant, so you can't factor it out. Okay, so you'd have to, what? What would you have to do? You'd have to plot V versus pressure and integrate to get the area under the curve. Okay, so and RT over P versus P. All right. Now, A and G, the Helmholtz energy and the Gibbs energy, are known as free energy functions. Okay, so in the so-called free energy representation, your fundamental equation is dA equals negative S dt minus P dV, and dG is negative S dt plus V dP. So based on these differentials, what partial derivative is equal to V? With respect to pressure, holding what constant? T. Okay. Now, how would you calculate delta G if pressure is constant, okay, and T changes from T1 to T2? So delta G, holding pressure constant, you're changing temperature from T1 to T2, so dt, right? Integral dt, what partial derivative goes here? partial of G with respect to T, constant pressure, right? So what would that be? That's really just the integral of this one, right? It's negative S dt, integral of negative S dt from T1 to T2. So if you have a way of, if you have an expression that tells you what S is as a function of temperature, if you can plot S versus temperature, the area under the curve will be from T1 to T2. So if you have S, if somehow you have a plot of S versus temperature, let's say, okay, then from T1 to T2, then the area under that curve would be integral of S dt. That would give you the delta G. Okay? Because you're integrating S versus time, versus temperature, sorry. Integral of S dt would be that area under the curve. Okay. So, what about this next question? How would you calculate delta G if T is constant and the pressure changes from P1 to P2? Integral from P1 to P2, d what? dP. What partial derivative we could put here? Partial of G with respect to pressure at constant temperature. And that's just integral of VdP, right? From P1 to P2. This one's easier for an ideal gas. What would it be? Integral from P1 to P2. What is V? nRT over P dP. Can we pull out P from this integral? Constant T. So you can pull out nR over nRT, right? It's a constant. So that's equal to nRT. What's integral of dP over P? ln of P evaluated from P1 to P2. So that's nRT ln P2 over P1. So that's delta G at constant temperature for a change in pressure of an ideal gas. Okay, so the pressure changes from P1 to P2. Since this is isothermal, what do we know about P2 and P1 in terms of volume? Boyle's law, right? Isothermal ideal gas, P1 V1 equals P2 V2. So we can also say delta G at constant T is nRT ln V1 over V2. Okay. Since P2 over P1, from here you can say that P2 over P1 equals V1 over V2. All right. Maxwell's relation. If z is a function of x and y, okay, we can write dz is something times dx plus something times dy. So this first something here is y. What is this? Partial of what? Partial derivative of what with respect to what? M is equal to partial derivative of z with respect to x holding y constant, and n here is partial derivative of z with respect to y holding what constant? X constant. So dz here is an example of what's called an exact differential. That means if you integrate it, you get delta z, okay? And when you have an exact differential, your cross-second derivative will not depend on how you take the derivatives. In other words, if you take the derivative first with respect to x, okay, and then take the derivative with respect to y, okay, same thing happens is if you take the derivative first with respect to y, and then you take the derivative with respect to x. It doesn't matter which order you do it. So the partial derivative of, what did we do here? M, to get M, we took the derivative with respect to Z, right? With respect to X, correct? So now, this is the derivative with respect to X. This time we take the derivative with respect to Y. That would give you a second derivative. How about this N right here? To get N, we took the derivative of Z with respect to Y. So this N is the derivative with respect to Y. So took the derivative with respect to Y. Now we take the derivative with respect to X. Either one of these two will give you the same answer. So let's illustrate that with this one right here. Let's say Z is equal to X cubed times Y squared, right? Just for example. What is the partial derivative of Z with respect to X? This is going to be our M, right? What is it? Holding Y constant. Y squared is a constant. And what's the derivative of X cubed? 3X squared. Okay. So what's this time let's take the derivative of M with respect to Y. Okay, you took the derivative first with respect to X. Now you take the derivative with respect to Y. This time holding X constant. What would that be? Three X squared will now be a constant, right? What's the derivative with respect to Y of Y squared? 2Y. So that gives us how much? 6x squared y. Let's do it the other way. Let's say N is partial derivative of Z with respect to Y at constant x. So what would that be? X cubed is taken as a constant. And what's the derivative of Y squared? 2y. Now, what's the second derivative, the cross derivative going to be? Partial of N with respect to, this time we take the derivative with respect to x, holding Y constant. And what do we get? We're going to hold that Y constant now. 2y. What's the derivative of x cubed? 3x squared. So that's 6x squared y. You can see these two are the same. Okay? So if you have an exact differential, your cross derivatives would be the same regardless of which order you take them. Okay? So if you have, let's say, negative s dg is negative s dt plus v dp. Okay? What did we say the partial derivative is? That's equal to negative s. With respect to t at constant p, right? And volume is partial derivative of 1. G with respect to p constant t. What's the Maxwell relation that we can derive from this? We're going to do cross derivatives, right? So this time we're going to take the derivative of this with respect to pressure now at constant T. And for this one, we're going to take the derivative with respect to temperature at constant pressure. Quick way to do this is to do this, okay, to set it up like that. So you can say now, if I'm going to take the derivative of negative s, this time with respect to pressure, the other variable, okay, it's holding what constant this time? T, right? So that's this one right here. That's going to be equal to the partial derivative of volume with respect to temperature, holding what constant? Pressure. Okay? So we can say then that partial of s, partial derivative of, negative partial derivative of s with respect to p at constant temperature is equal to partial derivative of volume with respect to temperature at constant pressure. This is a very important relationship that you can derive from the Gibbs, from the fundamental equation in the Gibbs energy representation. Why is this so important? Look at the right-hand side of this. That's a nice derivative. You like that derivative. It's just volume, temperature, and pressure. So this would give you a way of determining S, how S depends on pressure at constant temperature in terms of things that are more familiar, more easier, more convenient to deal with, volume, temperature, and pressure. Okay? So here's the question. What would you do to calculate the entropy change when a gas changes pressure at constant temperature? What would be my delta S here? Constant temperature, I change my pressure. So what do I have? Integral of, okay, I'm changing pressure. So from P1 to P2 dP, what derivative goes here? Partial of S with respect to P holding what constant? Temperature. But I don't like that derivative. I don't like that S. I'll replace it with this derivative over here from P1 to P2. So what's partial of S with respect to P at constant T according to our Maxwell relation? It's just negative of the partial of V with respect to temperature at constant pressure dP. And
how do you have dP with a constant P?
this is just the derivative at each point. So that's just the tangent, right? So let's just express this in terms of ideal gas law. What is partial of V with respect to T at constant pressure? Ideal gas. Do you recognize this? That's just what? Alpha, right? Times V. What's alpha for an ideal gas? 1 over T. Or if you want to go back to the basics, you can say V equals nRT over P, right? So what's partial of V with respect to T at constant pressure? It's just nR over P, right? Which is V over T, right? So that's nR over P, which is V over T. So let's rewrite this. Oops. Let's rewrite this integral right here. So this is negative integral of nR over P, right? dP from P1 to P2. Okay? So what would that be? Negative nR ln of P2 over P1. Okay? Or in terms of V2 over V1, since temperature is constant, P1 V1 equals P2 V2, right? So delta S for an isothermal expansion or compression of a gas is negative nR ln V1 over V2, or positive nR ln V2 over V1. If I flip V1 and V2, I make this positive, right? Isn't this the formula we derived earlier? Remember, before we even got to here, in the earlier chapter, we said for an isothermal expansion, W is what? Negative nRT ln V2 over V1. Remember, for a reversible isothermal expansion, and we said Q is negative W, so it's equal to, so reversible isothermal expansion of an ideal gas or compression. Negative W, so that's plus nRT ln V2 over V1, right? And then we said delta S is Q reversible over T because temperature is constant. So that's just going to be nRT ln V2 over V1 divided by T. Same formula. Okay, the same answer. Okay, so this is another way of arriving at that formula. All right, let's try this one. What partial derivative is equal to negative s? Partial derivative of what? A with respect to t holding what constant? Volume. And this is partial derivative of A with respect to volume holding what constant? Temperature. Let's do second derivatives to get the Maxwell relation. What's the Maxwell relation for this? Call it out for me. Negative partial derivative of, when you're doing Maxwell relation, you just look at this one. So S with respect to volume holding what constant? Temperature equal to, what's the other pair? P with respect to temperature constant volume. And again, what's the nice thing about this expression? Your right hand side here is just about pressure, volume, and temperature. Okay? And so here again you can calculate delta S when a gas expands at constant T. So what will we do here? We say delta S at constant T as the volume changes from V1 to V2. So this is going to be dV. What partial derivative I put here? S with respect to V holding what constant? Temperature. And I don't like that derivative, so I replace it with a derivative that I'm more familiar with. So that's going to be, oops, hold up. This should be negative, right? Negative and negative, so they're both. This is negative and negative. So this is going to be partial of P with respect to T at constant V dV. Okay, what's partial of P with respect to T at constant V dV? This formula, by the way, is generic. Okay, it applies whether you're dealing with an ideal gas, a real gas, a solid, a liquid. Okay, but for an ideal gas, what would that be? P equals nRT over V. So what is partial of V with respect, partial of P with respect to T at constant volume? nR over V, right? So this becomes delta S at constant T would be integral from V1 to V2 of nR over V dV, which will be nR ln of V2 over V1. Same formula we got earlier. Okay? All right. Now, remember we said last time I introduced you to the so-called thermodynamic equation of state. It tells you how the internal energy changes with volume at constant temperature in terms of just pressure, temperature, and volume. Okay? Last time we just assumed this, right? We're now ready to actually show it, to prove it. So we start with the fundamental equation, du equals T ds minus P dV. Okay, so what would happen if I divide these through by dV at constant T? I divide by dV at constant T. So divide by dV at constant T, dV at constant T. What happens? I get partial of U with respect to V at constant T equals T times partial of S with respect to V at constant T minus, what happens to dV here? Cancels out, minus P, right? So from the fundamental equation, we can get partial of U with respect to V at constant T is T times partial of S with respect to V at constant T minus P. Then you combine that with the Maxwell relation from dA equals negative S dt minus P dV. We did this earlier. What's our Maxwell relation? S with respect to V, right, at constant T is equal to P with respect to T at constant V. Why did I do that? Because I want to replace this. That's S with respect to V at constant T. That's this one. It's the same thing as this one. So I'm replacing that by P with respect to T at constant V. And that's your thermodynamic equation of state. This is what we introduced earlier. Okay, this is your pi sub T, remember? Partial of U with respect to V at constant T, your internal pressure. You can see it's called internal pressure. You can see its unit is pressure, right? So it's a pressure unit. And so, what would be the delta U when an ideal gas expands from V1 to V2 at constant temperature? How would you answer that question? Delta U at constant temperature would be what? Integral from V1 to V2 dV. What partial derivative goes here? This whole expression right here, right? This is partial of U with respect to V at constant T. That's pi sub T. So that's just integral of T times partial of P d with respect to T at constant V minus pressure dV from V1 to V2. And we did this before. What's the answer to this one? Ideal gas, isothermal, delta U is 0. Why is that? Because pi sub T for an ideal gas is just what? T times dP dt at constant V minus P, what would that be? That's NR over V minus P. That's P minus P. That's 0. Okay? And you can repeat that with the van der Waals gas. What would you need if for a solid? If you were doing this for a solid, what would you need? Then you're going to need an expression for this in terms of alpha and beta, alpha and kappa. You remember? So you say, in general, partial of P with respect to T at constant V times, remember our identity, this thing is equal to -1. What would these be? Okay, T with respect to V, and what's the derivative that goes here? Partial of V with respect to pressure at constant T, and what is this one? So this is partial of P with respect to T at constant V. That's what we want to solve for, right? What's partial of T with respect to V at constant pressure? It's 1 over alpha V, right? Remember, alpha is 1 over V partial of V with respect to T at constant pressure. And what is this second one? Kappa, if you recall, is -1 over V partial of V with respect to pressure at constant T. So this second one is negative kappa V is equal to -1. Right? So partial of P with respect to T at constant V is equal to alpha over kappa. It's a good relationship to remember. So another way you can write your pi sub T, your thermodynamic equation of state, partial of U with respect to V at constant T, this is pi sub T, right, is equal to T alpha over kappa minus P. Okay. So if you're dealing with anything other than an ideal gas, you'll have to know what you have to look up the alpha and you'll look up the kappa. Okay. And you plug that into your see how the alpha and kappa is affected by volume. at constant temperature. And then that will allow you to calculate your delta U. How much time do we have? We're past. Okay. All right, so we'll finish this up next time.